Hello everyone, and welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I would like to talk a little bit more about DC-DC converters and in particular a certain chip, a certain controlling integrated circuit that is, in my opinion, pretty promising. He is cheap, he is readily available on the market in large quantities, and he seems to be pretty flexible. A while ago, about 7 months or so, I made some first experiments with DC-DC converter chips, choosing a Texas Instrument very small integrated circuit that can go up to 7 volts maximum. Very popular 34063 chip and on pretty much equally popular LM2576 and others from this particular family of chips. Recently I wanted to study more about the 34063 because this one seems to be hackable, so to speak. The other ones cannot be hacked, they can only be used as they are. But this integrated, the 34063, seems to be pretty versatile. He's created to be an all-in-one chip that has both the controlling part and the switching element. However, because he's old, he has bipolar transistors for switching purposes, which are not very efficient. But the good thing about this chip is that he has all the pins available on the outside so that we can use those bipolar transistors so that we can control the maximum current circuit and do all sorts of things, and so that we can attach other switching transistors on the outside and turn this into a controlling chip only and improve his performances. This is what I will show you in this video, and this is what I will talk about. I will show you how I managed to go from 1.5 amps to 3.5, and in theory we can go even higher. And yeah, we will dive deeper into how this chip looks like on the inside and how he actually works. Okay? If you're interested, keep watching. Before we dive deeper, first of all, I would like to thank you for subscribing to my channel. I've recently hit 1,000 subscribers. I do realize that 1,000 subscribers is nothing for YouTube, but on the other hand, for me, it seems to be quite a number. There aren't all that many people who are able and willing to, watch other people explain things in 1 hour long videos, especially made by a guy who is not a native English speaker. It seems like most people nowadays just want entertainment videos and educational videos, and real do-it-yourself videos are not really all that popular. So thank you very much for subscribing. For me, this 1,000 this number 1,000 subscribers really means something. Also, before we move forward with everything I wish to show you in this video, please allow me to thank the sponsor of this video, which is PCBWay. PCBWay is a leading PCB manufacturer that can help you build your dream projects no matter how advanced they are. They can create just the PCBs for you or help you as well solder components on them through PCB assembly services. If you're creating a full device, they can help you create a plastic case through either 3D printing or injection molding services, or even CNC machining if you need a custom metal pieces for a metallic case. You're free to use your favorite design software, upload the Gerber files, and one of their professional representatives will contact you, offering you one-on-one customer service. All you need to do is go to PCBWay.com, the link is in the description. Thank you very much PCBWay for sponsoring yet another video, and now let's dive deeper into 34063, a chip that is pretty popular and has pretty good specifications. Mainly, he can work with 36 volts input and output. Well, the output matters less because we can have step-up converters that can go even higher. So the chip himself can work easily with 36 volts and has an absolute maximum rating of 40 volts, as we can see here. Okay, which is more than enough for 99% of projects, 99% of the DC-DC converters that we might want to create. He alone can be used for currents up to 1.5 amps, but as I will show you in this video, we can increase this maximum current. His maximum operating frequency is about 180 kilohertz, which again will be pretty good for the vast majority of our projects. We will most likely not go above 200 kilohertz due to various difficulties that we will encounter while trying to work with, I don't know, 300, 400, 500 kilohertz. It's not that they are impossible, but they are harder to work with. And this chip also has current limiting and is very, very easy to work with. So now let's take a look at the inside of the chip. And this is actually best done with an example, so that we can have the other components around. And we'll take the step-down converter, or the so-called buck converters, so that we can understand better what goes on here. I will make some print screens from time to time so that I can draw on top of the image. So what do we see here inside the chip? We have a few things that are basically they form the basic control circuitry of any DC-DC converter. We have a 1.25 volts reference regulator, temperature compensated, so internally this chip can perform accurate measurements of the output voltage and switch accordingly. We have a comparator with which we can verify, we can compare the output voltage, well, a fraction of the output voltage with this internal reference regulator. We have an oscillator, okay, whose frequency is constant and can be set by a single capacitor on the outside of the chip. This capacitor will basically determine the value of the frequency. This oscillator basically creates, I will draw it on the right side, creates somewhat of a ramp, a sawtooth waveform. Okay, my drawing is not very nice, but I will show you in a moment real print screens. Okay. And this oscillator basically generates impulses for controlling a set reset bistable, okay, and also an AND gate. This AND gate is on one hand receiving input signal from this oscillator, from the impulses created by the oscillator, and on the other hand receives impulses from receives a signal from the comparator that tells him whether or not the output voltage is above or below this reference voltage. This oscillator also has a nice feature besides oscillating, he is also able to change his duty cycle. So at the level of the triangle waveform, okay, the sawtooth waveform, the duty cycle will change depending on the current that flows through the entire circuit. And this is how these creators of this chip managed to perform overcurrent protection. Current flows through this shunt resistor that's found on the outside, okay? This is the positive input. The ground symbols represent minus, okay, from the input. The higher the current that passes through the entire circuit, the more voltage drop we will have across this resistor. Okay, the voltage drop is like this, with plus here and minus here. And the chip allows for 300 millivolts of voltage drop. Above 300 millivolts, the chip will simply turn off, because he will consider that we are in an overcurrent state. Okay. The functioning of this chip is pretty simple. Like I said, the oscillator under normal conditions generates a sawtooth waveform. This sawtooth waveform will be fed into an AND gate, and the other input, like I said, is from the comparator that tells the entire chip whether the output voltage is above or below the level that we want the converter to be, okay, to have on the output. If the voltage is below, then this comparator will basically give one logic on the output. And when we have an impulse here coming from the oscillator, so we have one logic on the other input of the AND gate, we will of course have one logic on the output of the AND gate, which goes into the set pin of the bistable. When the set pin goes to one logic, of course the output will also be one logic, which will turn on this Darlington pair of transistors, which in turn can either switch current through the inductor or do something else with other components that we might attach on the output. The absolute simplest form of DC-DC converter, of step-down DC-DC converter, is exactly like you see on the screen, with these two bipolar transistors acting as the actual power switch, switching on and off the current through the inductor. Okay. When the voltage on the output raises above this threshold, when the fraction of the voltage on the output raises above this 1.25 volts, and therefore our voltage on the output has risen above the level that we want, the output here, because this feedback voltage is fed into the inverting input of the comparator, this will be higher than the non-inverting voltage, which will make the comparator have zero logic on the output, and therefore this input, associated input of the AND gate, will be zero. Therefore, no matter no matter what input we have on the what value we have on the other input of this AND gate, the output will be zero. okay, the set pin of the bistable will no longer be held high. And at some point, when the oscillator will go, when the output, this output of the oscillator will go down into something that looks like zero logic, because the reset is inverted. Okay, this circle in front of the reset pin means inversion. Here we will have one logic on the reset pin, which will automatically make zero logic on the output of the bistable, and therefore shut down this Darlington pair of transistors, and therefore shut down the current through the inductor. Okay, and this is how the chip regulates voltage by turning on and off at a constant frequency but variable duty cycle based on output voltage here. And also, of course, based on where the sawtooth waveform of the oscillator happens to be at that particular moment in time. And also based on this overcurrent protection voltage. Because when this triggers, then the oscillator will change. Okay, now in order to understand a little bit better, let's take a look in very concrete terms at the circuit. I will make another print screen and I will start showing you images from the oscilloscope, and I will explain what I've done to obtain them. So, first of all, the voltage here across this capacitor that is required for the oscillator. If we are to just, of course, feed an input voltage, that's absolutely required. If we are to just ignore this shunt resistor and just make him zero, okay, just not connect anything. Of course, we connect the ground because we need the ground. If we don't do anything else, we don't care about anything else, and we just put an oscilloscope here across this capacitor, we will see something like this. Okay, I placed the chip on a breadboard. The breadboard, as we know, has some parasitic capacitances. Without actually placing any capacitor here, by just using the parasitic capacitances of my breadboard, which for some odd reason seem to be pretty high, or at least now in this experiment seem to be high enough, my chip has generated a 154 kilohertz sawtooth waveform that looks like this. Healthy, so to speak, sawtooth waveform goes from about 100 millivolts. We have 500 millivolts per vertical division, right? So this sawtooth, which is how a sawtooth looks like in normal functioning, goes from about 100 millivolts all the way up to, let me see, about 1.4 volts. Okay, regardless of the input voltage, regardless of the frequency, well, almost regardless of the frequency, the sawtooth oscillator waveform oscillates between these values, approximately 100 millivolts and approximately 1.4 volts. Now, we don't really care about this. This is just something nice to know, just in case we want to troubleshoot you know, how a circuit works with this particular chip. Now, if I actually added here a 100 picofarad capacitor, which adds over the existing parasitic capacitances in my breadboard, then the frequency has gone down to 90 kilohertz. But we see that for the most part, you know, the waveform oscillates still between about 100 millivolts and 1.4 volts, give or take. Now, if we want to really exaggerate just for the sake of seeing that things still work to some degree, if we put a 1 microfarad capacitor here, which is, by the way, not recommended officially, the waveform, the sawtooth waveform then changes dramatically and cannot go down below half a volt. The sawtooth waveform will oscillate between about half a volt and 1.3 volts. And the frequency has dropped down to 40 hertz. Obviously, this is not a frequency that's good enough for a switch mode power supply, but I was just curious to see how low can I take this. Of course, we cannot operate also with such a low frequency also from the perspective of this sawtooth waveform, because we will not be able to have very small duty cycles for the switching of the power switches here. Okay, so this is another reason why we will never want to work with very low frequencies. But nevertheless, it was something interesting, or at least I found it interesting to see how low can I take this oscillator. Okay, now next, we have seen that the oscillator works. Let me make another green screen. Okay. Now, on top of the oscillator, I also wanted to look at the emitter of the Darlington pair when I basically wire everything so that this chip considers that there's no output voltage and therefore needs to work at maximum, needs to do maximum work possible. So what I've done is essentially, of course, feed an input voltage here. I still had this resistor bypassed completely. I had pins 1 and 8 connected just like here in this image to the positive input rail. Okay, so basically I have both collectors. Well, I had both collectors of these Darlington pair transistors connected to the input. I had the output, which is this emitter, connected to a resistor to ground. Okay. Of course, I did not have the inductor or freewheeling diode, nor these feedback resistors, but I needed to tie pin 5 down to ground. Okay, so that here we constantly have 0 volts, so that the output of this comparator is 1 logic at all times, so that the switching of this Darlington pair is made entirely possible due to other factors, but not the output voltage. Okay, and the results were like this. So apparently 85% duty cycle is the absolute maximum duty cycle that this chip can have. Okay, normally it's not a problem, but just in case we will ever want to create a DC-DC step-down converter that can actually go up to the input voltage, well, now we know that this is not going to be possible due to the maximum duty cycle, which is 85%. Anyway, if that doesn't bother us, then this is the output voltage. Again, with yellow, we see the voltage here across this resistor. So whenever whenever the transistor is turned on, which happens pretty much at the beginning of the triangle waveform, then this Darlington pair gets to be turned on. By him being turned on, of course, he ejects current into this resistor, which in turn makes this output voltage go high. I had 5 volts on the input in this particular test that I've accomplished here, and of course we will always have a voltage drop here due to several factors, but especially due to the base emitter voltage drop of each transistor in the Darlington pair. So the output voltage will never be able to be exactly the input voltage. As we see here, we had 5 volts on the input. This is what I can tell you. It's not visible here. What's visible here is the output voltage is around 4 volts, so 1 volt less than the input. Not that it matters, I'm just explaining so that you understand, you know, why don't we have the 5 volts on the input. And yeah, and basically based on what the comparator does, what this comparator would do normally when he would actually have a feedback network to sense the output voltage, then you know, the duty cycle would decrease. Okay, and okay, and that's pretty much it in terms of very basic stuff. Now let me show you how I played with this voltage across this resistor. Let me make another print screen. So like I said, across this shunt resistor there will be a voltage drop directly proportional with the current that flows into this entire converter. Okay, in this particular configuration is the same current that flows through the switching elements inside the chip, then into and out of the coil, and so on and so forth. Now, in order for this chip to provide overcurrent protection, they have implemented this by essentially monitoring voltage with respect to the positive input pin, okay, that is allowed to go up to 300 millivolts. This was their design choice. Now, this is specified in the datasheet, but what is not specified is how exactly this works. And now let me jump all the way through here and show you a recording that I've done. Okay, I had the switching frequency around 90 kilohertz here in this particular experiment. And instead of, so let me show you, instead of here having just a fixed resistor that measures the current, what I did is basically I bypassed this whole thing so that I don't have a resistor here, but I placed here the middle point of a potentiometer. So let me draw like this. This is towards ground and this is towards the input pin. So I placed here a potentiometer just so that I can manually adjust the voltage between the positive rail, okay, and this particular pin, pin 7, because this is the voltage that is being measured by the chip and taken into consideration. So it's not a ground referenced voltage, quite opposite, it's a positive rail referenced voltage. And of course it makes sense because whenever we put a high side shunt resistor, we always have a positive rail referenced voltage. Okay, so I started from a voltage that is very close to 0, and we see this on the left side multimeter. This shows voltage in millivolts, and I will hit the play button, and you will take a look on the oscilloscope and see that we have the same 85-86% maximum duty cycle because I had nothing else connected on the output. Well, I still had, let me come back. So I still had a resistor placed here relative to the ground, and with my oscilloscope I was still watching this resistor, so that when these transistors get turned on, the voltage here goes high. Okay, no diode, no coil at this point in time. Nothing happens from 0 volts, well, 0 millivolts, all the way up to about 150 millivolts ish. Okay, which is half of this threshold voltage. Above 150 millivolts, something weird happens. First of all, the frequency will start to increase, but at the same time, the duty cycle will start to decrease because the off time will remain the same, but the on time will start to decrease. Okay, this explains why both the frequency increases, but also the duty cycle decreases. And when this voltage, and of course, at the same time, as we see on the screen, the triangle, the sawtooth waveform of the oscillator becomes more and more a triangle waveform that is balanced, and then will tend to swing towards the other extreme. Somewhere around 310-320 millivolts. Okay, I'm doing my best. This is 319 millivolts here. Somewhere between 300-320 millivolts, the chip will turn off completely the oscillator, so that everything shuts down, because at this point he considers that there's too much current flowing into the circuit, so he needs to do something about it. So he needs to shut down, to stop switching current into the inductor, therefore to stop the transistors. Okay, this is definitely a nice way to, well, in my opinion, okay, I'm not an expert, but I find this a nice way to protect against overcurrent, because the protection does not start abruptly. Okay, it's not an on-off thing, it's a gradual protection. And I think overall this this improves the fluidity of this circuit. Yeah, so this is how the overcurrent protection works. And now let me show you a modified version of this step-down converter that I have created for the specific purpose of overcoming the maximum current. Now, I have only created this circuit on the breadboard. Okay, so I will show you the actual results. You will see that the ripple was a bit too big. This is because I just wanted to make a demonstration. I did not use a proper capacitor on the output. I do not have proper circuits. I have many. In fact, I can show you right now. This is basically my circuit. As you see on the upper side, on the center, the transistor, which is placed on a small PCB, the MOSFET switching transistor, is connected with crocodile cables to the Schottky diode, which is in the center, and then with other crocodile cables on 40 or 50 years old capacitor from Soviet era magnetophones, an electrolytic capacitor that, well, still works technically speaking, but you know, he doesn't really have a good characteristics anymore, good performance. So overall, you know, the performance of this particular converter is not going to be very good, as I will show in a few moments. But again, this is just for demonstrative purposes. So what do we want? We want higher current. Okay, what do we need to do in order to achieve higher current? Well, we need to stop using those let me get back. We need to stop using these Darlington pair transistors as switching elements, because these cannot pass more than 1.5 amps. Even at 1.5 amps, this chip gets a bit too hot. So yeah, we need to make this circuit, this chip, be only a controlling circuit, not also a switching circuit. So for switching, we need an extra transistor. We need a separate transistor. And I chose a P-channel MOSFET because these are the easiest ones to work with in a buck converter. In order to turn them on, they act as PNP bipolar transistors. In order to turn them on, you have to drag their gate down towards the ground. And in order to turn them off, you take their gate and you bring that closer, as close as possible to the source, preferably quite at source, so they have 0 volts gate to source voltage. Okay. So how do we accomplish that? Well, we accomplish that with bipolar transistor that is turned on from a resistor on the positive rail side, and by him being turned on, he short circuits this source of the MOSFET and the gate, and therefore keeps at all times, or will tend to keep at all time, this MOSFET turned off. This is something that we want. We of course do not want to have the opposite way of MOSFET being mostly turned on and turned off by the controlling circuit. Now, of course, from time to time, we will want to turn on this MOSFET, so we will want to pull the gate down towards the ground, and this is where this extra diode comes in handy. We already have inside, you know, our chip bipolar transistor that can handle pretty good currents, pretty high currents. So we don't need an extra transistor just to, just to provide higher currents. We only need a diode. When the let me make okay. So let me make a print screen again, so I can show you. Okay, so when this switch point, okay, pin 1 and 8, which is which are the two collectors of this Darlington pair. When these collectors are when these transistors are turned off, therefore these collectors don't drag down at all, because we have pin 2, which is the emitter of this Darlington pair, in this case connected straight to the ground. When the inner Darlington pair is turned off, then current will be able to flow through one, polarize and open transistor 2, which in turn will make a short circuit between these two pins, and therefore this MOSFET will be turned off. However, when this point gets pulled down because the inner transistors turn on, then two things will happen at once. First of all, some current will be able to flow through this diode and basically take the gate of the MOSFET and drag her down very close to the ground. And at the same time, this will not be a problem. This will not create a short circuit because you know, this transistor's base emitter junction will be inversely polarized. Therefore, this transistor will be turned off. Okay, so yeah, this is how the whole switching happens. And now, in order to have higher current, all we need to do is essentially choose a better MOSFET here. And I choose YJUS 9435A simply because, well, this one was a cheap channel MOSFET that can resist 30 volts, which is good enough for me, and a maximum of 5 amps. Well, 5 amps at 25 degrees Celsius, and at 70 when the transistor will get hotter, this can resist only 4.1 amps at the very best. I will show you in a moment some tests done, and because I haven't had the proper cooling for this MOSFET, which is very small and looks more like an integrated circuit than a MOSFET, I kind of burned him at around 3.5 amps or so. Anyway, yeah, why did I choose this model and also the chip 34063? It's because these are very, very cheap and readily available components on the market. You know, I'm not advertising anyone, I'm just showing you one of my electronics distributors. If we take a look at this controlling chip 34063, first of all, we see that 100 pieces cost only 20 euros, so basically 20 cents per piece. And at least if we buy, you know, larger quantities, which is a good price. And also the quantity available on the market right now is way more than we could probably need. It's in the order of multiple tens of thousands of pieces in stock. Okay, so we see here this particular submodel, because this model of chip 34063 has several submodels and is being produced by different manufacturers. So here we have 12,000 pieces on stock, here more than 2,000, here more than 3,000, here almost 15,000, 6,700, 1,000, almost 2,000, and so on and so forth, 4,500 here. So as we can see, we have this chip only from a single manufacturer. We have this chip in a very large quantity, in the order of tens of thousands. Of course, the other manufacturers will potentially have even bigger stocks of this chip, so this is definitely an advantage, as well as the price. Like I said, the price is pretty good, 20 cents per piece. That's nice. Also, this p-channel transistor, right now, at the moment that I'm making this video, there are almost 8,000 pieces in stock only at this particular distributor. But when it comes to MOSFETs, it doesn't really matter all that much. You can take pretty much any MOSFET that can resist the current that you want him to resist, and also the dissipation power that you need him to resist. Okay. At 100 pieces, this is almost 9 euros, so basically it's 9 cents per piece per MOSFET. And so yeah, these are very nice qualities to have, very nice attributes. And what follows is the classical configuration of an asynchronous step-down DC-DC converter. Asynchronous meaning, the reverse switching is done automatically by this diode SR540. This is a Schottky diode which can resist 5 amps and 40 volts. This is why this model 540 has been chosen. 5 amps, 40 volts. Okay, I wanted to create a DC-DC converter that can go up to 5 amps or close to 5 amps, and for the most part I achieved. I also placed here a 220 microhenry inductor that can work with 5 amps of current. Of course, the output capacitor and 500k potentiometer to adjust the output voltage. The one thing that I still did not do is put a shunt resistor here on top to protect this entire circuit, because again, this was only for testing purposes. In practice, if I would want to actually use such a circuit, I would need to add perhaps a few more components, and of course add protection. Now, this chip does not have inbuilt under voltage lockout protection or any other forms of protection. However, those will be easy to accomplish with just a handful of outside components that will hack into one of these pins. Okay, most likely the peak current pin 7. And this is pretty much the entire functioning of this step-down converter. Yes, he does have a little bit more components than the usual configuration that is being presented and recommended by manufacturers. However, this is the price that we need to pay for just being able to have almost any current on the output that we want. And in a future video, I will show you how to create step-up converter that can work, can offer on the output an even higher voltage than this chip allows. Okay. So now, before I finish this video, let's take a look at the rest of the demonstration. Okay, so here we have the circuit in a very do-it-yourself manner with a lot of cables and crocodile cables. Like I've shown you earlier, I have 5 volts set on the output, 12 volts on the input. Right now, no current whatsoever. The current will be the one, the output current will be the one that you will see in this yellow right hand multimeter. Okay, and from time to time I will also show you the ripple with the yellow line, the ripple on the output voltage, so that you know what's going on. Okay. I, of course, have an artificial load connected to this entire circuit, so I can draw current from the output and see how everything behaves. Okay. Somewhere a little bit around. So the like I said, because I'm using some rather unorthodox components and methods of connection, the ripple is not your typical triangle wave ripple. It looks a lot worse than that. But again, this is just for demonstrative purposes. Also, because the peak-to-peak voltage ripple will be relatively high, in the order of 200 or 300 millivolts or so. The output voltage that is seen by a very simple rudimentary multimeter like this one will appear to drop from 5 volts to 4.6, 4.7, something like that. Okay. Now I have turned down the current. So before, I don't know if you saw, I managed to get up to 3 amps of current. Okay. And things were working. Again, with the minuses that I've just explained, but things were working. And meanwhile, I decided to turn it down to 0. Check the temperature to see with my bare hands to see, you know, if temperature is still decent, in decent range of values. And then I went on to draw even bigger currents, and I will show you how at 3.5 amps, because, you know, my MOSFET transistor wasn't cooled properly, he got burned, and I've got pretty much, okay, so now here you see 7.72 jumped from 4.7, 4.6 ish, and then very quickly goes to the full input voltage. Even when I turn down the current at 0, this is a clear sign that I've burned my MOSFET. But doesn't matter. The experiment has been proven successful overall. Okay, so like I said, let me show you again here. A chip that alone can only go up to 1.5 amps. Here he can reach 3. Even 3.6 almost without a problem. Of course, until he burns. But it's not the chip's fault, it's the transistor's fault. Basically, from now on, based on what transistor we use, we will be able to have higher power or lower power DC-DC converter. Of course, that's not the only thing that we need to change, but, you know, as an idea, we can turn this chip into just a controlling chip and have all sorts of nice converters. So this was pretty much it. I declare myself content with what I've achieved so far with this test. So this will be at the very base level of many of my DC-DC converters moving on into the future. I hope you learned something new. I hope you've enjoyed this presentation. Thank you very much for watching. I would also like to thank those of you who support my work on Patreon. Your support is most welcomed. For those of you who would like free support, please subscribe to the channel and hit the like button. It does help the YouTube algorithm present my videos to other people who might be interested in them. So, thank you very much for watching this video, and I will see you soon in the next one. Bye bye.